alongside with understanding move semantics that we've already looked at. It is also important to understand how memory is allocated and freed when we create and destroy variables in various ways, why manually dealing with memory can quickly become a mess, and how smart pointers help us avoid this mess. So let's dive in. When we declare variables, they have to be allocated somewhere, which essentially means that they need to find a big enough free slot in memory to fit into. Once we stop using these variables, we want them to free the memory that they occupied so that it could be reused. Otherwise, we might run out of free memory and be unable to create any new variables whatsoever, which we'd really like to avoid. This act of allocating and freeing memory is usually called memory management. Some languages, like Python, Go, Java, or C#, just to name a few, deal with memory management in an automatic fashion by using the so-called garbage collection system. The system runs at intervals in the background and searches for the variables that are not in use anymore and frees their memory. We can observe this by looking at the amount of memory used by programs written in such languages while they are running. The amount of allocated memory will grow for a while, followed by a sharp drop once the garbage collection is triggered. We won't focus too much on garbage collection here though, but if you'd like a more in-depth look into this, please feel free to follow a link to a post about various options for garbage collection in Java that is linked below this video. And while such garbage collection system is convenient in terms of not needing to think about memory on our side, using it takes away from the performance of our program. These systems must perform a scan for unused memory repeatedly at runtime. Furthermore, it is hard to predict when these scans will happen and how long they will take, so garbage-collected languages are not well suited for safety-critical applications, where we need to know exactly when each operation takes place and that they all fall within a certain time budget. What makes C++ suited for such safety-critical applications is that it stays away from garbage collection-based memory management altogether. Instead, it takes a two-tier approach. On the one hand, it makes a good use of scopes and makes sure that any simple small variable allocated within a scope gets freed by the end of it in an extremely efficient manner. On the other hand, for some variables that need to allocate a large chunk of memory or that have to be still available after the end of the scope in which they were allocated, it allows us to allocate and release memory manually at our discretion, which in turn allows us to implement any behavior of arbitrary complexity. Here I have to mention that with great power comes great responsibility, and historically, most of the fear of C++ among the beginners came from this ability to manage memory manually. It was complicated to think about how this manually allocated memory should be managed, and especially when it should be freed. There was also a lack of good tools and guidance that would be universal for each and every situation, which made learning how to work with memory safely hard. But thankfully, those days are in the past. And that's where modern C++ really comes into play. You see, today we have these tools within the standard template library, or STL, as well as the accompanying guidance on how to use them that work for nearly any situation that we might encounter. Using these tools and following the best practices allows us thinking more abstractly about what we do. Not when to allocate and free memory, but what entities we want to create, who owns them, and how their ownership should be transferred while the program runs. This makes reasoning about our programs much easier while keeping our code efficient and memory safe by default. But before we talk about these tools we have at our disposal to manage memory in modern C++, let's briefly focus on the basics, on what happens under the hood when we want to create or destroy a variable. And while common, this task is anything but trivial. Remember that we want to find a perfect place in memory for every variable we want to use. These variables can have vastly different sizes and lifetime durations, which influences their optimal placement in memory. Furthermore, we usually want to avoid fragmentation, which means that we don't want to have many small holes between allocated variables. If we have those, it might be that we have a lot of free memory in the absolute sense, but we're still unable to find a continuous chunk of memory to allocate some larger variable into. This means that ideally we want to find for each variable being allocated the smallest free memory slot it fits into. Solving this problem in general is very hard. Think about it. We can't scan all the memory at our disposal exhaustively every time we want to allocate a variable. That would take too long. But we can find effective algorithms for finding not perfect but good enough spots, granted that we have some more knowledge about our data. For example, we might notice that a lot of scope local variables we use are really small variables like ints or floats. They're allocated and freed within their scopes very often, which means that ideally they should be allocated and freed very quickly. Considering that these variables are mostly small in size, and that our scopes are mostly quite short, at least, well, they should be, it is a feasible assumption that we should be able to fit all of such small local variables into a relatively small continuous chunk of memory. So we designate a small part of our memory, typically around 8 megabytes on Linux and macOS, to managing such local variables. Furthermore, because these variables are always allocated sequentially and get deallocated in the reverse order of their allocation at the end of the scope, we use a stack-like data structure for managing where to place them in memory. Just like a stack of coins allows putting and removing coins from the top of this stack, such data structure supports putting and popping variables at the end of the currently occupied stack space. This mechanism is used under the hood for all the local variables we create and destroy in our C++ programs. And just to get some more intuition, let's look at it a bit more precisely. We'll use an example, as we always do, and this example does not follow any of the best practices we've followed throughout this course. Furthermore, it leads to an undefined behavior, so please don't copy this example to any real projects. But it does serve us well to build an intuition of how stack works. In this example, we allocate an int with a value of 2 on a stack, followed by a variable of type int pointer that points to nothing, or a null pointer. Then a new scope starts, and we allocate 2 integers in a static C-style array without initializing them. Please don't use such C-style arrays in real life, but I do need them for illustration purposes here to make this example simpler. We set the values in that array in the next 2 lines. In C++, standard C-style arrays are equivalent to pointers, and we can set pointer to point to the start of our array data. This is not a great idea in modern C++, but it is a good indicator of where things are on a stack for us. If we now print all values, we'll get the expected output of 42 followed by 23. However, everything changes once we leave the inner scope. Once we leave that scope, all the variables allocated while in it get popped off the stack, which means that now pointer points to some data that we do not control, and this leads to undefined behavior. And if we run this program, it might print anything that it finds under that address. This way of dealing with allocating and freeing variables is amazing for local data. As long as the data does not need to persist beyond the end of the scope, this data structure is extremely efficient. We always know exactly where to allocate new memory and which memory to free at constant time. No additional runtime operations needed. Many things change the moment we want to allocate bigger chunk of data at once, or for our data to persist beyond the end of the scope. Pause for a moment and think if we can keep such data on the stack too. In the case of a bigger chunk of data, the answer is obvious. Once the data stops fitting into the stack, we can't allocate it. If we try to allocate progressively more data on the stack in a loop, the program will terminate with sig-seg, which means that we tried accessing memory that is not allowed for us to access when trying to allocate beyond 8 megabytes of data. Now, what about persistent data? Let's for a moment assume that we could keep a variable in our stack for a longer time. And let's also assume that we allocated it in the middle of some scope with some normal stack variables allocated before and after it. By the end of the scope, we must free all memory of those variables, which essentially means that we would need to pop all the variables above our persistent variable, then copy our variable somewhere, pop the rest of the normal variables, and copy our persistent variable back. Not only this is not elegant, but we also had to copy a potentially large chunk of memory around, which is slow. This situation is similarly bad if we would want to free the memory of our persistent variable at some manually chosen point. This would mean that we would need to copy everything that we put on top of it in the stack, remove the persistent data we want, then copy everything back on top of the stack, which is also slow. And we don't like slow. As you can imagine, the situation would be even worse if there would be more of these persistent variables we wanted to keep track of, which is actually typically the case. So clearly we want to keep our stack quite small, therefore we must find another way to find a place to allocate potentially large persistent data. Such a place needs to be able to accommodate variables of any size, from small to very large. Also, allocations should depend as little as possible on the amount of data allocated before or after. Finally, such allocations should generally be made explicitly by the programmer, as only they know if the particular data should persist and for how long. When we speak about allocating these data, we usually call these data being allocated on the heap. Those of you who know data structures might think that this is related to the heap data structure, a binary tree with a parent having a larger or smaller key value than its children. And indeed, I could imagine how the free chunks of memory could be organized as such a heap data structure by size to optimize the search for a free chunk of a given size. But that seems to be not the case, although the evidence is murky on this one. If we trust Donald Knuth, one of the gods of algorithm design, this name is just coincidental. But I could not find any definitive proof for either side of the argument, so if you have it, please send it my way. And while you're at it, please subscribe to this channel. It really shows me if I'm moving in the right direction with these videos. Anyway, the easiest way to think about the heap is an intuitive one. Imagine a heap of stuff, like coins. Every coin represents a place where we can store our variable, and let's say that its denomination indicates the amount of free space available. So when we need to create a new variable on the heap, we look through our heap to find a coin that represents space big enough for our variable and store our variable in that found slot. In our analogy, this effectively removes the found coin from the heap, maybe adding a smaller coin in its place. This obviously takes some time, but once such a place is found, the variable can stay there in that memory until we don't need it anymore. So allocating on the heap is definitely less efficient than allocating on the stack, but it has a benefit of being able to allocate or deallocate these data at any time with less consideration on how packed the rest of the memory is. Please note that this is a very inaccurate analogy, as there is much more stuff happening under the hood, and the actual implementations of the heap allocators are well optimized and, as a result, quite complex. But thinking about heap of coins gives a decent enough intuition, and that's all I'm aiming for here. We allocate memory on the heap manually in C++. For that, we use new and new array operators that take a type and derive the amount of space that we want to allocate from that type. The new operator allocates a single variable, while the new array allocates an array of those. In order to free the memory, we need to call delete or delete array, respectively, on the pointer that points to the memory allocated on the heap. To have a bit more hands-on experience, let us see how our previous example changes if we use the new array instead of allocating a C-style array directly on the stack. We start by pushing the size and the pointer to the stack and enter the inner scope just as before. What is not as before is that we now use the new array operator to allocate our array on the heap. We only allocate memory for it without initializing the stored values, so initially it stores garbage data. Note that the pointer to these data is still stored on the stack. Now we update the values stored in our array and set the pointer to point to the same address as the array, which allows us to print the values using the pointer variable. Different from the example before, when we leave the scope, only the array variable is cleaned up from the stack, but the pointer variable still points to our data, which still happily lives on the heap. So we can still print all the values we stored in our array using the pointer without any undefined behavior. Finally, we can explicitly free the memory using the delete array operator on our pointer variable, and at the end of the program the stack empties itself. There is a number of common pitfalls when using heap allocated data, and you could probably have already guessed this from the amount of screaming smileys in my code snippets. If you followed my lectures for a while, you know that I'm not a fan of taking care of things manually. I just don't trust myself on that. If we use new and delete operators manually, like in the example before, we have to be very careful with them. If we forget to call delete on the data that we allocated with new, we get a memory leak, as the memory we allocated is never freed. And even if we do call a delete, we can still mess things up. If we allocate an array using the new array operator and free it with a normal delete operator, we will only free the memory under the first element of our array. So memory leak again. Although in this case, at least on a modern Clang compiler, there is a compilation warning about this situation. So please make sure you have warnings enabled and that there are no warnings left unhandled when you compile your code. Another common mistake when working with raw pointers is to try to copy the data by assigning one pointer to another. But this does not copy the data. This only copies the pointer. So instead, we now have two pointers that point to the same data. So let's say we remove pointer 2 first. Now pointer 1 points to the memory that was already released. If we try to delete it, now we will get a runtime error that will tell us that we are trying to free the memory twice, and thus a double free. If we initially allocate two objects, the situation becomes even worse. Not only we have the same error as before by freeing the memory twice, but we also introduce a memory leak, as we now do not have any pointer that points to the data originally stored under the second pointer, so we can't delete it. In addition to this, if we don't follow best practices, we might have no way of knowing if and how we should free the data under a given pointer. Let me illustrate. Imagine we have a bunch of functions that all return exactly the same type. Int pointer. It is impossible to know if we need to free the memory that the returned value points to by just looking at that pointer alone. And yes, we might get lucky and these functions might all have descriptive names, of course. Our functions clearly state that they allocate memory and also what they allocate. So we know that we should use delete operator to free the memory of a single allocated variable under pointer 1, delete array operator to free memory allocated to store an array pointer pointed to by pointer 2, and that we should not touch the memory under pointer 3 as that memory will be freed by the pull struct. However, let's be honest, life is rarely as accommodating in the real world. Functions might change their implementation with time without updating their names to adequately reflect these changes, or they might not have readable names in the first place. This way, we must look into the implementation of these functions to make out what they do. This is already quite annoying, but we still technically can find out if we should free the memory and with which operator in each of these cases. But note how hard it is to track the correct delete operators even on such a small example. Imagine having a huge codebase riddled with code like this. But we're not done yet. Oh no, there is more. If you remember the lecture about libraries, you know that the actual implementation can be hidden from us in a compiled library in such a way that the only thing we see is the declaration of the function. Now there is no way for us to know what to do with the pointer we get. I hope I scared you enough, and you never want to allocate and free memory manually ever in your life. And this is a great attitude, trust me. There is a solution to all of these problems. In the lecture about object lifecycle, we already touched upon the RAI principle that stands for Resource Allocation is Initialization. This principle is crucial for writing safe C++ code. Essentially, we need to make sure that all memory allocation happens at the time of object creation, ideally in a constructor, and that memory is released on object destruction, combining this with properly implemented value semantics, such that these objects can be copied and moved safely, and we can pretty much guarantee the overall memory safety. This is essentially what happens in the STL containers, like std_vector or std_string. They wrap a raw pointer to some heap allocated memory and dynamically manage it, including resizing it when required, moving the pointer to it during the ownership transfer, and eventually cleaning the things up when they get destroyed. So we can work with variables of these types as if we had simple local variables and let these classes handle all the memory-related stuff under the hood. But what if we have our own custom data that we want to allocate on the heap? Well, we could write a wrapper class that would allocate our data, handle all the move semantics, and eventually free its memory, but there is a better way. Now is eventually a good time to talk about smart pointers. They are RAI containers with proper value semantics out of the box, so that we don't have to implement such value semantics from scratch. Furthermore, there are different flavors of smart pointers to model different types of ownership. Nowadays, we mostly use standard unique pointer and standard shared pointer. So let's talk about these a bit more in depth. These are classes implemented in the standard template library, or STL, under the memory header. They are designed to be an almost drop-in replacement for raw owning pointers while providing guarantees for memory safety. The standard unique pointer is our main workhorse when we need to create data on the heap. The idea is extremely simple. The standard unique pointer offers unique ownership of a raw pointer given to it. That means that This unique pointer is the only entity responsible to free the memory under its pointer. The way this is achieved technically is by making sure that the copy constructor and assignment operators of standard unique pointer are deleted. This way, a unique pointer can only be moved, not copied. There are never two raw pointers that point to the same memory owned by this unique pointer. We work with an entity of such a unique pointer in a very similar way to how we usually work with a raw pointer. The standard unique pointer is a class template which we can instantiate for any wanted type, here integer. We can either directly call its constructor passing a raw pointer to the memory allocated with new, or we can use a helper function, standard make unique, that helps us hide the naked new away and has benefits in terms of memory safety should something go wrong during the allocation. Once created, we can access the values under our pointers by dereferencing them with the star operator, or in case of classes, we can call their members with the arrow operator, just like we did with raw pointers before. We cannot assign pointer 2 to pointer 1, as the copy assignment operator is deleted for standard unique pointer, which protects us from performing a shallow copy by mistake. But we can move assign one into another. This way, the memory initially held by pointer 1 is freed, and pointer 1 takes ownership of the memory previously owned by pointer 2. When pointer 1 dies, it frees the memory it owns, so no need to call any delete on our side either. In addition to this typical pointer-like interface, we also have access to functions like .get, which gets the underlying raw pointer, and .reset, that allows to reset the smart pointer to own a different raw pointer. All in all, standard unique pointer is an extremely useful tool. Use it all the time when you need to allocate some persistent data on the heap. It mimics raw pointers very closely, without any of their downsides and costing us nearly nothing at runtime. If you are interested in why I said nearly, then watch this CPPCon talk by Chandler Knuth. It is an amazing talk about what we call a zero-cost abstraction and why they probably don't really exist. Another smart pointer that is extremely popular is the standard shared pointer. As the name suggests, just like standard unique pointer models unique ownership over some data, standard shared pointer models, well, shared ownership. Under the hood, it is also a RAI container, but unlike the unique pointer, it does not delete its copy constructor and assignment operators. Rather, standard shared pointer implements the so-called reference counting under the hood that keeps track of how many instances of this shared pointer point to any particular underlying data. If a new copy is created, this counter is incremented, and if some instance is destroyed, it gets decremented. Only once all of them are destroyed, meaning no one points to the data is freed. I hope that you now see why the ownership is shared. Any of shared pointer instances can be the last surviving one, and so can be the one that removes the data. And whoever removes the data owns it. We create a standard shared pointer in a very similar way to a standard unique pointer, by either using its constructor that also takes a raw pointer, or using the standard make shared helper function that allocates the needed object under the hood. Note how, as opposed to the unique pointer, we can copy a shared pointer to another shared pointer. In addition to the interface that a unique pointer provides, we can also see the number of pointers that point to our particular place in memory by calling the useCount function, which in this example will show that it is incremented in the inner scope and goes back to the old value when we leave that scope. Finally, as a bonus, smart pointers, being, well, pointers, are polymorphic. So we can create a standard unique pointer to base from pointer to a derived type, just like what we discussed when talking about inheritance. In this example, pointer 1 say hello will call the base implementation, while the pointer 2 say hello will call the overridden derived implementation, just as we expect. I'll leave it up to you to check if this also works if we use a shared pointer instead, though. Now, this is about everything one needs to know about memory allocation and smart pointers. At least this is about 99% of the knowledge, with the rest available at cppreference.com. Was it too much? Tell me what you think. All in all, we should almost never allocate memory manually. A good rule of thumb is to never write a manual delete, which leads us to also almost never write a naked new. And we should never have to deal with a memory leak or a dangling pointer in our life again. And on that positive note, I'd like to, as always, thank you for your time. Please consider telling your C++ inclined friends if you found this useful and you think they might like it too. It would really mean a lot to me. And if you would like to look deeper in how you might use pointers in a polymorphic way in C++, then please give this video a watch. While if you'd rather dig deeper into how move semantic works, then give this video a go instead. Thanks again, and bye.